number is ELEC-OSC-S1B, the LC oscillator basics. The circuitry today we will be discussing. We have defined already the oscillator as a device which converts a DC electrical energy into AC electrical energy. Here's another definition. We can define the oscillator as: the oscillators are the electronic circuits that generate a continuous periodic waveform at a precise frequency. Oscillators convert a DC input, that is the supply voltage, into an AC output, the waveform, as we already defined in the previous talk, section S1A. So we can have this output waveform have wide range of different wave shapes, frequencies that can either complicated in nature or simple sine waves depending upon the application. So oscillators are also used in many pieces of test equipment, producing either the sinusoidal sine wave, square waves, sawtooth waves, triangular wave shape waveforms, or just train of pulses of a variable or constant width. LC oscillators are commonly used in radio frequency circuits like the transmitter and receivers because of their good phase noise characteristics and their ease of implementation. An oscillator is basically an amplifier with the positive feedback or regenerative feedback, that is the feedback signal is in phase. This feedback we have already discussed in detail in the classroom lectures. We have already done that, and one of the many problems in electronic circuit design is stopping the amplifier from oscillating while trying to get oscillators to oscillate. This means that normally what amplifier, when we are designing, our main emphasis is to fix the Q point on the load line, not disturbing the state of that Q point. But in this case oscillator, we want the oscillations. So these are two things which you have to look into that. So oscillators work because they overcome the losses of their feedback resonator circuits, either in the form of capacitor, inductor, or both, in the same circuit by applying DC energy at the required frequency into the resonator circuit. In other words, an oscillator is an amplifier which uses positive feedback that generates an output frequency without the use of an input signal. The oscillators are self-sustaining circuits generating an periodic output waveform at a precise frequency, and for any electronic circuit to operate as an oscillator, it must have following three characteristics: some form of amplification, that's amplifier be there, positive feedback, the element to feedback the signal, that's the regenerative feedback, a frequency determined feedback network, that is the particular frequency of that network as well. Okay, so let us now take into the basic. You can read out an oscillator has a small signal feedback amplifier with an open loop gain. Open means open loop. The circuit is open circuit over there. Open loop gain equal to or slightly greater than the greater than 1 for oscillations to start, but to continue oscillations the average loop gain must be returned to unity. That means the gain is AV is equal to 1, means output is equal to input. Is the ideal situation. So unity means that normally AV we write as equal to output to input voltage ratios. So if both are equal, then we get the unity. In addition, these reactive components, that is the XL and XC, the reactances have got the capacitor, an inductor, an amplifying device such as operational amplifier or bipolar junction transistor is required. So operational amplifier is the one which performs the operation of addition or subtraction, while we have done this bipolar transistor amplifier in the past. So unlike an amplifier, there is an external AC input required to cause the oscillator to work, as the DC supply energy is converted by the oscillator into AC energy. So in amplifier, normally we have got that input AC signal which is amplified the output, but in case of the oscillator, we don't have any input AC signal. So we need AC signal from the LC tank circuit, which is fed at the input at the base and is amplified. Now this is a simple basic feedback oscillator circuit. We have done that in the block diagram, but this is also another way it can be represented. This is the amplifier symbol. We represented that as a main amplifier in the block diagram. So the output is fed back to this is called the sampling network, which the feedback network. From the sampling network we take to the feedback network, and is fed back to the input, which is added with the input V input minus beta V output. So feedback signal is being added. In the case of regenerator, it should be positive, but anyway, we have got the two signals are mixed together, plus or minus, depending upon if it is regenerative, it will be added; if it is degenerative, it will be subtracted. So here this is a very simple layout for the feedback oscillator. The gain of the without feedback is given as AV is equal to V output divided by V input. Let me show you. Here is the gain output divided by this input. This is the actual amplifier gain. This input is supposed to be going in here, but what we do, we introduce a mixing network over here, which adds the feedback signal with the input and fed to the amplifier. So the relations we have done in detail in the previous topic in the class. So we come to the here. This is the final result, which is the gain, which we represented as AV. Here it is giving it as a GV, which is given as A over 1 plus A beta. We have derived this relation in our last lecture in the class. So the oscillators are the circuit that generate continuous voltage output waveform at a required frequency with the values of the inductors. The waveform at required frequency with the values of the inductors, capacitor or resistors. The forming a frequency selective LC resonant tank circuit and feedback network. So you see, you can go through that. This is just a criteria given how the oscillation should start, when it should not start. So when beta is less than 1, or AB is greater than 1, or AB is equal to 1. So these are the values, the conditions for the oscillations to take. The LC oscillator frequency is controlled using a tuned resonant inductive circuit, L circuit, with the resulting output frequency being known as the oscillation frequency. By making the oscillator's feedback a reactive network, the phase angle of the feedback will vary as a function of the frequency, and this is called the phase shift. Now there are basically two types of oscillators. The sinusoidal oscillators, these are known as harmonic oscillators and are generally called as the LC tune or feedback or RC tune feedback type oscillators that generates a purely sinusoidal waveform which is of constant amplitude and frequency. The second type is the non-sinusoidal oscillators. These are known as the relaxation oscillators and generate complex non-sinusoidal waveforms that changes quickly from one condition of the stability to another, such as square wave, triangular wave, or sawtooth wave type waveforms. So the two we will be, in our case, we will be discussing only the sinusoidal oscillators. This is not in your course. Non-sinusoidal oscillators are not in your course. So we will be discussing only sinusoidal oscillators. Now let's see the how the oscillator resonance phenomena is depending upon various factors. When a constant voltage but of varying frequency is applied to a circuit consisting of an inductor, capacitor, and a resistor, the reactance of both the capacitor resistor and inductor resistor circuit is to change both the amplitude and the phase of the output signal as compared to the input signal due to the reactance of the components used. Reactances are given as inductor reactance XL is equal to omega L, XC is equal to 1 over omega C. So you can see they are frequency dependent, and the frequency changes with the same frequency. The frequency increases, the XL will increase while the XC will decrease. If the frequency decreases, now the XL will decrease while XC will increase. So at the highest frequencies, the reactance of the capacitor is very low. So that is, if the frequency is very high, omega is very high, 2 pi f, so XC is small, okay, while the XL will be high. So in this case, XC acting as a short circuit while the reactance of the inductor is high, acting as an open circuit. Suppose if omega is very high, let's say infinity, so XC omega is very low, so that's 0, then XC will be equal to the infinity, where XL will be equal to 0. So vice versa, we can put the values, and that will give that XL and XC output values. So the reactance of the inductor is high as compared as if you put higher here, it will be low. Let's say infinity, that will be equal to low. XC is equal to 0. Infinite, if you put omega, so XL is equal to infinite, means open circuit. This will be acting as a short circuit. So at a low frequency is now the inductor resistor circuit is to change both amplitude and the phase of the output signal as compared to the input signals. So okay, we were here. Now at low frequencies, the reverse is true. The reactance of the capacitor act as an open circuit, and the reactance of the inductor act as a short circuit. So low frequency means if we put here omega is equal to 0, it will be infinite open circuit. Here XL is equal to 0 times L, which is 0 ohm, which will be a short circuit. Now between the two extreme combination of the inductor and capacitor produces a tuned or resonant circuit that has a resonant frequency FFR, is actually a subscript, in which the capacitive and inductive reactances are equal. XL is equal to XC and cancel out each other effects, leaving only the resistance of the circuit to oppose the flow of the current. This means that there is no phase shift, as the current is in phase with the voltage. So consider the below circuit. Now this is the basic LC tank circuit we have discussed in detail. Here the DC voltage is applied. When switches to the point A, the DC will charge the capacitor to peak value. When it is connected with the point B, so it will discharge discharge, the capacitor will discharge on the inductor. Expanding magnetic field and collapsing magnetic field will cause the exchange of energy, or the oscillations of the energy to and fro between the L and C. So that has been discussed in detail, so you read it out, no need to read it again here. So you just go through that. That is the part we have discussed in the previous topic. So let's move on to the this section, which is now the damp oscillations. There is a what we have this oscillatory action of the passing energy back and forth between the capacitor C to the inductor. The would continue indefinitely if it was not for the energy losses within the circuit. Electrical energy is lost in the DC or real resistance of the inductor coil, that is ohmic resistance. Now in the dielectric of the capacitor and in radiation from the circuit, so the oscillation steadily decreases until they die away completely and the process stops. I were to mention over here the credits for these tutorials. The same topic which are in your course are given on this tutorial website, www.electronics-tutorials.ws. You can also visit this site and see the same tutorials over there, and can just read out these tutorials as well. So now then, in practical LC circuit, the amplitude of the oscillatory voltage decreases at each of a cycle of the oscillation, while eventually die away to zero. So here we have, this is the damp oscillation, means actually what happens that I have also discussed that in the previous topic S1A, that there are oscillations die in actual case, and for sustained oscillation we need a feedback, so we provide the feedback signal so we can have the sustained oscillations. In this case, if the resistance of the circuitry, ohmic resistance, is small, then you can see the takes longer time to die. It is sustained for a longer period. But here in this case, if R is large, then it is heavily damped, means quickly die. This, you can see the time period over there. It is taking longer and it is taking shorter to the dying of the signal. Okay, so at resonance takes place at XL is equal to XC. So let's discuss the resonance part. Here this graph is showing that the XL with the frequency plot. This is XC also along with the frequency. This is the difference of the two, XL minus XC, the two reactances. The resonance takes place here, FR, at XL is equal to XC, while you can see by increasing frequency, the XL, you can see here, is increasing, while at the same time the XC is decreasing. So this is a beautiful graph showing that if one quantity frequency changes, the two quantities are also affected by their values, that is XL is equal to omega L and XC is equal to 1 over omega C. So this part is when XC is greater than XL, we have this section, and this is where XL is dominant over the XC. Here XC is dominant over the XL. So that is the resonance part. If you remember, we have done a practical as well, and also we have discussed this in the RLC series resonant circuit, and the other, that graph we have in case, let me check that one. Okay, so that graph, the resonant graph, was also there. We have discussed that resonance peak value at the FR. So let's move on to further the resonant frequency. We have also calculated this at L is equal to xc. What we have, the final value is given by, this is the final resonant frequency, Fr is equal to 1 over 2 pi LC. So L is the inductor, C inductance, and C is the capacitance, and Fr is the resonant frequency. Now let's move to the basic circuit, basic transistor LC oscillator circuit. This is the main circuitry. Let's move to that. Okay, this is the circuit with a bipolar junction transistor. You can see this transistor is of the type common emitter, and it is NPN transistor, because arrow is not pointing inward but it's outward. Okay, NPN, non-pointing in, as I already explained that in about the BJT transistor section when we were explaining this, the construction and other things. So we have this is the collector, this is the base, this is the emitter. So the emitter is common, this is a common emitter transistor amplifier. This is the base. At the base there is L2 inductor. This is in the collector we have connected the LC tank circuit. So L is the inductance and the C is the capacitance. So this is the block diagram of the same amplifier. This is the amplifier. Okay, when oscillations are produced, they are fed to the input of the amplifier, okay, from L, and there is a feedback. Then what we have, this is the connected to the collector here. So from the collector, this L is mutually coupled with the L2 here, you can see also. So this small portion from the output is fed back to the input here. So this is the input here, L2, which is coupled with electromagnetically. This induction induces the induced EMF in the secondary coil, which is L. In this case, the L is the secondary coil, and there is a core in it. We can change the mutual inductance in this case, so that we can change also the frequency, resonant frequency as well. So you can see one thing here, that when the signal is fed at the input, it amplifies the signal, but it produces a 180-degree phase shift. But we need a regenerative feedback, means it should be in phase when it is linked with the secondary coil is L to the tank circuit. So what we do, we select L2 such that it produces a phase shift of 180-degree, which is then in phase with the signal in the LC tank circuit, and sustained oscillations are obtained in this case. That's how the electronic circuitry of the transistor amplifier is used in the feedback oscillator feedback schemes. So what we have, this is the main phenomena of involved in the electronic circuit of the oscillator. So rest this whole description is given, the same description is given. You can read it out carefully, and you will find it quite helpful. Let's do one example, very simple example, that an inductance of 200 millihenry and capacitance of a capacitor 10 picofarad are connected together in parallel to create LC oscillator tank circuit. Calculate the frequency. So that is the resonant frequency. So frequency, it may not be resonant frequency, but frequency is for that particular values. Normally it is resonant frequency we look for. It is a resonant because L and C are those, this is the resonant frequency relation. So what we have to calculate the resonant frequency of oscillation is 1 over 2 pi square root of the LC. So we get the 112.5 kilohertz So the rest below is given the summary. You also read out that summary. Will give you the update that in a short paragraph that whatever has been discussed in the whole topic. Okay, with this we reach to the end of the topic. We will inshallah meet again in the next with a new topic next time. Till then, Allah Hafiz. Thank you.